Brought to you by Connect.js, Atlanta's premier JavaScript conference. Sponsored in part by FeatherDirect. Need a mobile app? Contact us for your custom mobile solution.
All right, so this is a really content-rich topic, and this is a really compact slide deck. There are a lot of things to cover and a lot of really details around immutability and advanced React that are geared toward application building. So this is part 3 of a 3-part talk, where the first part would cover basic React, how React works, life cycles, top-level API, and JSX. The second part would be an intermediate React course. It would really focus on reusable components, add-ons, passing properties down through children, and some of the nuances that you get into when you start building React components, because it's a different way of thinking. But the part 3 is really the most interesting part, and this is a focus on application building. So this is not just, here's some views. This is a actual application, and how do you reason about data? How do you reason about data flow through your application, and specifically immutable data? So that's going to be one of the biggest topics. That really, the two biggest things today are data flow through React and immutable data. So we're going to spend a lot of time talking about these things. But because this is an advanced talk, I understand that there may not be a lot of React in production. So I guess, who is actually using React right now? Is there anybody? Is anybody using it in production? Yeah. So basically, that's my team right there. So we're going to start with the problems that React solves. We're going to understand the basic elements of React, but we're not going to see hello world. We're just going to understand React from an architecture. We're really going to focus on JavaScript processing versus DOM manipulation. This is where React gets such speed, performance, and where you can really game React to get high-performance web applications. And that's really the focus, is that we're dealing with large data sets and a structured application, and getting your DOM to be as responsive as possible. One of the keys to that is immutability. So again, the first two things that you're going to get, the main focus of this is data flow and immutable. So before we begin, I'd like to say thanks to the leaders of these topics. These are Rich Hickey, the author of Closure and ClojureScript. He's a really big proponent of immutable data. David Nolan is doing great things in ClojureScript and immutable data and high-performance React through Ohm. A lot of these principles he founded, and he's really blogged about, and they are part of this ecosystem. And then Pete Hunt from Facebook has done a lot of good videos just explaining React. So find these names, remember these names, find their videos. They're a wealth of knowledge. And who am I? I'm a full-stack developer at Ayres here in Atlanta. I work in Java and JavaScript all day. I build single-page applications in Backbone, and now, over the last year, we've switched entirely to React. React is wonderful. So if you haven't played with it, give it a shot. If you do any kind of event-driven MVC, it is worth your time. All right. So everything that I'm going to do today, the slide deck, all the examples, there are tons of examples, are on GitHub. This is the one link that you need to copy down. Everything else is there for you to take home. I've done a lot of work for you to be able to, I understand that these are concepts that maybe you can't absorb right now. So you can take these home and work through them and really get to the same conclusions I have, that React can be extremely performant. All right, and benchmarking. So benchmarking is coming up with some reference point for performance, and then using that reference to tell how fast something else is. So we're going to be benchmarking React components. And it turns out this is amazingly simple with React because they have a top-level API called render component. Its third parameter is a callback, which can resolve a deferred to tell you that your React component has completely rendered the DOM. This is amazingly simple. If you try to do something like this in an event-based framework, it starts getting really soupy, and you either have to instrument your code or change your code to figure out when the actual DOM is completed. So this is really nice. You don't have to touch your code. It's just built right in. And immutability. So high-level concepts layered on top of React, layered on top of any framework that you're using in the DOM is immensely powerful if you can stick around to the end, like I said, this is a lot of content, you're going to see a 200% improvement by just dropping in something like immutable. That's just something that we can't ignore as an industry, and it's something that's really being pushed in functional languages, but it's really something that's going to change the way you think about programming, so it's important. And in fact, it's so important that I'm going to spend more time on immutability than I am on React, because React as an application has certain ways to game it. So we will be looking at that. But before we begin, let's just spend a few seconds talking about where we came from. And in 2010, Backbone was created. It was really stable in October, and it changed a lot of things. It really gave us a way of structuring a web application. And that is probably the biggest claim to fame that it has. That, and it is one of the event-based MVCs. So you probably work with one of these right now. But at the end of the day, you're just observing models and handling events. Data changes, so after you render your view, data changes are manual DOM manipulations. You have to find where that data lived in the DOM. You have to update the DOM. And not only that, but as the data changes, which view cares about that data? These are problems that exist in event-based frameworks because data doesn't flow through the application. Data is listened to. It's not defining the API. So you get something that looks like this, where your views and your data are more like soup. Right? You can't tell the flow through your code. It's not reasonable. And there are a lot of good talks on Flux and why Flux hammers this out. We will cover some of that. Okay, so now let's think about React, or not React, but Backbone building this. This is just a small view of a 10,000 cell table. It's fixed with, so we won't have the reflow issues when we render this thing. But if we think about it, we would have to render a table. We'd have a table component in Backbone. We'd loop over all our rows, and for every row, we would loop over our cells. And so each one of these would be a TD tag, followed by a TR tag and a TD tag. But as data changes, we have to register handlers to figure out which one of these elements has changed, right? So in our row view, we will listen for the row of cells and say, okay, well, this value is different now. So I will find the value in the DOM. I will call my cell view to say, what's your new DOM? And then I will manually add it to using jQuery. The problem is that nothing's acting as a friend for you because you're having to do all this by yourself. And not only that, but if you manipulate lots of data at once, you have all these views touching the DOM, processing as fast as they can. Right? There is no structure here. They are listening to data, and they are responding in the DOM as fast as they can do it. And the impact is that you can't really see who's listening, that views are indirectly related to other views, and that what views actually depend on in your collection. And not only that, but when you're dealing with an application, it's really hard to get someone up to speed by just showing them a router, because they make a change, and unless you have lots of really good tests, a change to data or a change to a view may not actually register correctly in other views that aren't indirectly related to this data. So this is where Flux and and React really shines, because simple is maintainable. And what we really want to say is that we never have these small incremental DOM updates, right? We just always re-render our entire state. So that means a full page refresh to to every other framework except React. The way that React is going to work is that a data change is no different than an initial render, in that you're just giving a render, or you're just producing a virtual DOM, the entire virtual DOM for your application. And then that virtual DOM is diffed against the actual DOM, and then it's put into a queue. So if we are on initial render, the queue that's going to be, or the DOM queue, is going to be the entire table, if we stick with our table example. But on a partial reference, that DOM queue is only going to contain the find and replace method of the single cell that changed. But we're going to do the exact same code. This is idempotent. This means that we can take a test, we can give it state, we can render our component, and then we just assert the DOM. This is all we have to do. We still have to exercise our event handling and the components within it. But we do not need to do anything more than this worldview, because we have idempotency built in. All right, so React is an always re-render framework. And one of the big powerful things is that React render method, which is going to produce HTML in a virtual DOM, is going to be diffed against the actual DOM. And this diffing is extremely performant because it's a tree diff. This means that as soon as a parent node is unequal in each of the trees, the entire subtree can be queued for update. We do not have to process. So at the top node, we instantly know to replace the DOM. We do not have to process our virtual DOM. We get huge speed improvements. And this is really how React gives you these incremental changes without having to handle them yourself. So the initial render looks just like this, just like a cell render. So if I'm going to produce an entire table of 10,000 cells, I'm going to get my virtual DOM. It's going to be a table full of 10,000 cells, 100 rows, 100 cells each row. I'm going to look at the differences between what's in the DOM using tree diff, which is extremely fast. And maybe if I change one cell, the leaf node of one of my virtual DOMs is the only thing that's different. I'm going to put in my queue a find and replace for that node. And this is what's really interesting about React is that this queue is a strategy-based queue. And you're not having to do this at all, but you can change the strategy that this queue operates on. It batches your DOM manipulations for you. It's not just going to go to the DOM as fast as you want. We're actually going to, in all the examples that you have, we're going to be using request animation frame strategy because we want to slow React down. We only want it to do the work that actually is displayable. If we let it use this native, it's actually too fast. So we can slow it down and produce a DOM that gives us exactly what we want, doing a full render every time. All right, it has a declarative syntax, but the really big thing is that it's idempotent, right? Is that one data produces one result. There is no in between. JSX is XML and JavaScript, and this is how we're going to basically be able to go to Bootstrap. If you like Bootstrap, you can take their examples, plop them into a render function, and basically render. I mean, it's that simple. It is XML. It is HTML. It is hierarchical. And it has the full power of JavaScript. Your views are no longer indirectly related to something that sits in a resources folder. It's defined here. And because of that, you can use JavaScript. Right? You can really use all the tools you can, or all the tools you have, and all the tools that you know. You don't have to use underpowered for loops or ifs. You can use full power of JavaScript. And synthetic events are just going to hammer out and make it level playing field for all the APIs. So you don't have to worry about old versions of IE, new versions of IE. You're just going to have a simple common API for all eventing. And under the covers there, synthetic events that handle for you. OK, so that was good. That was basically the beginning, right? So this is now the beginning of advanced React. OK, so we're going to start with React as a central, or really as a core concept of application state. And as you start modeling your application, you want your APIs for each component for each React component to be as small as possible. You don't want him to carry the weight of the entire app state because he's not reusable, right? If I'm just a header, why do I care about all the users? If I just want to show some piece of data, that should be my API. So this is really where we're going to talk about application flow. So we have an app state, which this is again just an example that has users and states. So our app component is what we call a root component. This is where everything happens. It's also in Flux what they call a view controller. He's going to get the entire application state, and he's going to manage the application state. And what he's going to do is he's going to map over the users, let's say. And he's going to create user components and give them just a single user JSON object, right? But that user object is really part of a global application state. And I may be changing a user object that another component, let's say states, also take in users, but they also take in states. I need all these components to listen to each other and talk to each other because I may mutate data, part of a global application state that my other components need. Right? This is one of the hardest things that when you start dealing with React is how to communicate data. right? You have a unified directional flow of data, but you need changes to be replicated across all listening parties, right? But we're going to do this in 3 ways, and these are not the only 3 ways. In fact, cursors are an immutable concept, but they could be replaced with any kind of eventing. The 3 primary ways are you can bind to a parent, which means that we're going to let the parent handle data mutation for us. So a calling React component will handle it. We're going to define cursors. And cursors are basically pass-through application states. So these are pointers within a global application state that can remain in sync with a global application state. So now when you say, I get a user within a user's list, and I change it, that change is reflected globally, and anybody who cares about that change automatically knows that it changed. But in React, it's not a reactionary, right? We're not listening for that change. We're just going to render the change. Our application state as a whole is going to completely change, and we're going to re-render the entire component. And then Flux is going to give us a loosely coupled API and kind of take this and make it more suitable for application building, more scalable, more, I have a new developer coming on, what's my code base, how do I actually reason about this? Let me sit down, and this will show you, okay, well, I can go look at my stores, and I can look at my actions, and now I have a reasonable understanding about how my data flows. All right, so this is our example model. This is what we're going to use for the next, to build out those examples. And it's really simple, right? We have an application state which just has a header, and we have a parent component, and he's going to render and produce a DOM. But in order for his DOM to be produced, he's going to ask the child component to render part of his DOM. Right? This is a standard thing anybody's done. If you've done Backbone, this would be like a subview. And then this is the code in the parent, right? So if we're on the bind, then I have a render, and I'm going to render a header in an H2 block, and I'm going to call to my child component. I'm going to pass him 2 things. I'm going to pass him an update handler. So I'm going to pass him a function reference. And I'm going to pass him the actual data. Now this is why, this is what we're talking about when we say reusable components. Now this child component has an API that's defined such that you have to not only give it data, but you have to give it something that changes that data. It's not in control of its data, right? Its API is larger than itself. It's really too much. But this is how we do that, and this is in a lot of the beginning React. This is kind of the model that you work with. Is that okay? Well, I'm going to render a child. So here's how to update this, because properties are not changeable. Okay, so in our child, you can see that this is it. This is my render. I'm going to render an input. My value came from my parent, and my change handler also came from my parent. So I'm not going to do anything in my child. And if we go back to the parent, see that the change handler is just going to set properties given a new header value. This is very simple, and this is probably the first attempt at data flow within your application. Another example of this, or another way we could do this, is through cursors. And again, this is a way to keep data in sync, global data, without having to change and make our API for our child components so large and basically not reusable. So before I really talk about, just jump right in, I need to kind of take a step and show you some tests, right? To actually show you what cursors look like as data, and really show you what immutable looks like. So a cursor, in the next few tests, we're going to see that what's equal and what's not is using immutable is. So this is the data equality. This is not referential equality of these immutable objects. This is the underlying data. And this is exactly how, when we put this in React, how it's going to decide if things are equal to. So immutable is for all intents purposes, equal for today. All right, so a basic immutable principle would be that I've defined an array of 2 value objects, and I've assigned it to X. He's immutable. If I unshift onto X and I add something to the front of his list, I'm not changing X. I'm going to produce a new list. And now I'm going to assign it to Y. And then if I take Y and I unshift something onto it, I'm going to produce a new value, and it's going to be Z. And then we expect that X was not changed, Y was not changed, and Z has the full list. So this is an important property because referential integrity is maintained here. Right? X is still equal to what it was before. It cannot change. It's immutable. You cannot change it. You can only generate new data. All right, so now let's look at a spec. So to generate immutable objects from Immutable.js, which is the library behind giving us immutable data structures, we're just going to take an object, we're going to call from.js on it, we're going to produce an immutable object. It's the same object, it's just represented immutably. When I call a cursor, when I make a cursor from my immutable object, I just say .cursor, and then I can assert that these two are equal. There's no difference. It's just I have special properties as a cursor I did not have as data before. But my data is still the same. My object is the same, and I can operate it on it in all the same ways. Okay, well, now I can update a cursor and preserve my immutable data. So again, I'm going to create a cursor from the same data. I'm going to set something on the cursor. So I'm going to change the Pi to a Raspberry Pi. But it's going to produce a new data, and you see that that the immutable foo and the cursor are still referencing the same data. Their data hasn't changed. They're both immutable. And that the cursor and the new data that was produced from setting on the cursor are not equal. And the only thing that actually references this change is what was generated, and that's the new data object. And he's immutable as well. Okay, so here's an even more interesting one, right? We're going to allow multiple updates to happen within a single transaction within a cursor, because just setting, just updating data one at a time, triggering a full page refresh might not be the best thing. Because again, we're going to apply these concepts to React components and data flow. So we have a foo object, and again, it's the same foo. We're going to create an immutable object from foo, and this time when we create our cursor, we're going to give it a callback. And the callback is going to register and basically rewrite the cursor object so that we can keep operating on the same cursor. So when we say update, I can update pi and I can update portion, all within this update method. And now my cursor is equal to both pi and raspberry and small. My original foo and my cursor now are not equal. And in the GitHub repo, you'll see that I put a spy on transaction, and it's only ever called once. So we're only ever going to get a refresh or a transaction call when we're only going to ever get one. Is basically it. So what's the upshot of this? Is that now we can create cursors from cursors, and we can start passing those down within our objects, within our components. And so when we start testing and when we start setting things in child components, we'll actually get updates on our main cursor. So here, our transaction listener is going to set the main cursor. We're going to create a cursor with a transaction. We're going to call it main. And then we're going to create another cursor from it, just looking at the pi. And then when we update pi to be raspberry, our main cursor is now different. This is really important because this is the data flow now. So our central app is still there. We're going to start carving up the pieces that we need. We're going to pass just a user object to a component, or just a section. We could pass whatever data we want to a component. And as they change it, we're going to be listening for it in the application context. And we're going to receive a transaction. And that transaction is going to flow back down. All right, so when we plug this in as an architecture inside React, we have to do a few things. When we mount, when we did mount, we're going to set the state, and we're basically going to create a cursor. So my application state is in my properties. I was given that. And I'm going to use my state here to represent my cursor. Again, you see the same on transaction listener. But this time, instead of just resetting the value of cursor, we're going to set the state, replace the state that cursor was pointing to be the new value. And our render function now looks a little bit better, right? Because I just ask for the header, and then my child components API is just the header. He does not need a second event handler to mutate this object. And so in the child, this is what I would expect, right? The child who's going to do the change actually controls the change and writes the change. This is much cleaner. And we're not going to call set properties because we actually cannot do that in React unless you're a top-level API. So we're just going to mutate property. The transaction listener is going to listen and propagate that change. All right, so a demo of both of those things. And I can't play movies inside of this. So basically, what did we just build? We built the same thing. I mean, we built this, right? that code is exactly doing this. Nothing different, they both do the same thing. All right, so let's try to do it in Flux. Let's do something that actually scales, that actually reasons about, because when you start dealing with cursors, you're going to start getting into race conditions, because what if something changes data that you're trying to change? How do you actually control that? There is no gatekeeper, right? So cursors are great for smaller applications, but you really need something like Flux to be the traffic cop, to say, I'm going to change this store and make sure that whatever I rely on also changes. And make sure that the other actions that are coming, the other changes that want to make changes to the store, queue up behind me. Don't let them just take their data that they have and React, actually give them the new data, right? So it's going to do unidirectional data flow and give us more reasonable flow. It's only composed of 3 things: actions, dispatchers, and stores. And it's a pattern. It's not a framework. You can go and get a Fluxor implementation, and you can go and get from React the actual dispatcher that they provide. But at the end of the day, it's just a pattern. It's going to be implemented in many different ways until it actually calms down as an industry and we figure out what Flux really means. Right now, I feel like we're still figuring it out. So actions are going to be exposed to views. We're going to trigger updates on stores. They're routed through a dispatcher, so they have no direct dependency on a store themselves, and they actually have no implementation. They're just a, hey, do this, and here's some data that go along with this, right? A dispatcher is going to take that action, and he's going to marry it with a store, and he's going to manage the dependencies between the stores, so that if you say that update the states object before you update the users, because maybe I'm adding a new state that the user is going to need for me to update his address. It's going to manage the interaction, and when it's done, it's going to emit an event. And that event is just like our on-transaction handler in a cursor. It's something to let us know, something to register against, that data has changed, that our global data state has changed, and we need to re-render. All right, and then a Flux store. This is really, if you came from a backbone background, you're used to domain modeling, and that was something that was really hard to let go of when I first started with React, is that I liked having collections and models, and I liked having a rich domain. Flux stores give that back in the sense that all your application logic is going to live there. You no longer have a view that that really controls your application state. And that is a pattern that you will start doing if you don't incorporate Flux and states or stores in your design. At the core of a store, it's a singleton. It's just one data, and it's going to emit events once the data has been changed. Here's the flow, and this is really a step in the right direction, because now we don't have this kind of everything talks to the top. We have everything just reaches out. Everything just says, okay, well, here I am, and I want something. Or here I am, and I want to issue an action, and I can issue an action from anywhere in my tree, from any subcomponent. But if we stick with the same example where we're trying to update a header, we would issue an action. It would be dispatched. The store would say, well, okay, here's my new header value. I'm going to set that on the store. That's my new header. And then that change listener is being listened to in my app component, and my new app state is defined, and I will re-render everything. And this is really the can slide, right? An action is going to go to a dispatcher. It's going to figure out which stores are involved, and it's going to update a view. Views are going to react to that change, and they're going to say, well, hey, I have this other action that I want to do. And this is where Flux is really in that state of what's going to happen, because the dispatcher here is implementation. Implementation is going to say, well, okay, views that circularly define action should be basically queued up. They should wait until the previous action was completed. Now I can process my queues, but that is an entire implementation detail. But this is the general Flux design, and this is the only design. There is no view model controller, right? There is no soup. So let's look at the actual implementation from the same one. If we took bind and we took cursors, well, let's do it in Flux. So our action, again, doesn't have an implementation. He's just going to dispatch, which again is through the dispatcher, a type of action, an update header call, and then some payload, a value, the new header value. This is simple, right? The store is a stateless, or is a singleton, so he has state defined. We've merged it in with an event emitter, which is just part of what Facebook gives you, or I guess this is a node module. And we're going to do a couple things. We can emit a change, and this is going to be using the event emitter's prototype. We're going to set the header, and we're going to be getting the full application state, because maybe, again, this is our domain model, right? We're not just going to set header in a real-world application. We're going to be setting and mutating lots of things within the store. And finally, we're going to register a change listener so that our view can register against this store and get updates based on changes that we make. All right. Our stores also register with the dispatcher. So this is a nice architecture because you can change the implementation of your dispatcher without needing to change both the actions in the stores. This is a really nice architecture that's found in things like Spring, and I really think this will be scalable and this will work. And it's simple, right? Like, I'm going to say, when I receive an action of update header, here's what I'm going to do. I'm going to set the header value, and then I'm going to emit a change. There are other constructs here built in, like wait for. I can wait for other stores to update. I can do other things, but this is the most simple case. And when we plug it in to the parent object, things get a little bit simple, right? My default properties is just my app state from my store. My component did mount. So after I've fully rendered once, I'm going to say register this change listener, and whenever something changes, or whenever my app state changes, reset my app state. A reset or a set props or a set state will cause a full re-render of your component and everything below it, everything that depends on it, or that it needs to render. And then the render function is as simple as it was with a cursor, in that we're just going to pass down state. All right, and then in the child, again, this looks a lot like the cursor implementation. I have my property coming down as my value, but I have my change handler being defined within my child. And all I'm going to do is I'm going to emit an action. So instead of actually calling set state on this, I'm going to send it through a traffic cop that can do more scalable things. It can handle 2 or 4 or a whole set of children updating the same data at once. And this example, I'm not going to go through based on time, but this example is in the repo. It's called Flux Buckets, and it's basically a complex application that models application state, and it models component state. So there's a difference between your global application state and what your actual, and variables that are defined in each component. And this really exemplifies that and gives you a more non-trivial example of Flux. All right, so this is probably the most interesting part to me of this talk. And this is where we're going to explore tables and really explore performance in React. And this is, yeah. So we're going to model a 10,000 cell table as a single React component. So we're not going to use some of the best practices like composability. We're just going to literally write a single React class and have it render this 10,000 cell table. Then we're going to try to use better practices of React, better practices in software development as a general, and break these things out into more composable materials, like a table view, a cell view, and a row view. And then we're going to compare them, benchmarking, and we're going to see what we get. At the end of the day, the single React component just looks like this. I have an app state, which has rows in it, and then it has cells in each row, and my table component is going to render the entire table. So here's what the base render method looks like. He's going to create a table element, and he's going to map over the rows. In the same class, there's a render row method. He's going to get the row, and he's going to map over his cells, creating a single TR element. In the same class, there's a render cell, and he's going to produce a single TD, and he's going to put its value in it. This is pretty simple and basic React. Now the interesting part, right? We said that we could benchmark React, and this is exactly how you would do it. I have a single component. I'm going to randomly update a single value every cycle, and then I'm going to re-render my entire component. This is a 10,000 cell table. So this is really nice. This is going to give us empirically, how do we actually build React, right? What does it mean to actually do that? All right, so here's this test running. It doesn't matter how fast or how slow it is, or even the result of this benchmark. What we're really looking for is a general feel for what the performance was. Okay, so I updated a small set of these elements, and I was really able to do 11 operations a second using this benchmarking. Okay, so let's use that as our base case. So if we just did the minimum amount of work to create this table and to re-render it fully every time, we were able to do 11 operations a second. Okay, and if we look at the flame chart, we can see that we're about 100 milliseconds every React render. And this is actually not that bad. This is pretty small. Depth means Java processing, width means time. So the Java processing time is not bad. This is a nice flame chart. Okay, so now let's model it with best practices, right? Let's actually take our app state and let's create a table. And let's create row components, which are going to be given a rows array for that row. And then for each row component is going to be responsible for creating the cell components. So now we have a nice composable architecture, and let's just look at how we actually implemented that. So as a table, we're going to, again, make our table element, and we're going to map over our rows. This time, instead of rendering the rows right here, we're going to actually call to the row component. Row component, here's your API, here's your cell, and key is a way to make sure that React can keep track of this cell on the DOM. All right, so now in the row component, a separate component, his render function is create a TR element and map over all the cells that you were given. And for each cell that you have, call a cell component, giving him his API as a cell. And again, we have a key. And then the cell component can't be simpler. It's really just a TD with the contents of the cell. Okay, so who thinks this improved things? All right, let's see. By the way, there wasn't that many hands up. Sorry, I can't read this thing. Okay. Okay, here's the same code that we just saw using the same benchmark, and it's visibly different. There is not as much happening, actually. And it turns out that this is over half slower. All we did is just model it with different React components, or model it with the best practices that we have, and it's twice as slow. That sucks. What actually happened here? I mean, we're dealing with React where before we had a single component that React had to keep up with, a single virtual DOM, a single element that React was keeping track of for us. Now, we have 10,000 plus elements that React is actively trying to manage for us. Not only that, but they're going to produce and store a virtual DOM representation of each one of these components for us, and we're going to check that virtual DOM every time we render to see, do I actually need to render? And this is the best we can do. This is a lot deeper, and this is a lot slower. It's twice as slow. It's interesting, but we can fix this. We can fix this in such a way that, I mean, it's just impressive. But we have to do it with immutability, because what we have right now is we don't have the tools to do it. And this isn't a React problem. This is a data set problem, right? This is, my data is large. React is doing exactly what we told it to do. I'm not having to render that cell update. I'm just giving it, I've just changed my application state and said render. He's doing the most efficient way he can based on what I've given him. So now I can give him an even more efficient way of managing state. And that's through immutability. And really immutability principles are best left to the experts. And so David Nolan has a great talk on immutability. If you're interested, find me at lunch. I'll give you the link. I'll even put it on this repo. I'll update the repo with it. But we're going to talk about persistent data structure, structural sharing, Immutable.js library, which is what's going to power our immutable data. And I don't actually have that link slide. So Facebook is putting money into immutability because immutability is going to change everything. Immutability takes a large memory footprint, but it improves the performance immensely. And David Nolan wrote Ohm, and if you're a CoffeeScript or a Clojure scripter, you know that Ohm is really fast. It's really nice. It's just a big difference to jump into a Lisp-based language than it is for JavaScript. So thankfully, we have two libraries that we can do immutable data structures with, Immutable.js from Facebook and Mori from David Nolan. But they both operate on this principle that my data, my JSON data, is going to be represented as a tree. It's just internally mapped as a tree. And when I try to change that immutable data, I'm going to create a new tree node, and I'm going to try to reuse every element in that tree that I can. And I'm only going to ever create any subtrees or any new nodes that don't already exist in the tree or have changed in the original data. So this is incredibly powerful, and we're going to see that through some testing. But let's look at a simpler case, right? Because this is really what all I'm qualified to talk through is structural sharing. Right? We can analyze this piece, and we can all reason about it. So here we have a list of 4 elements. We're going to have X be the first 2 elements, Y be the last 3 elements, and then Z be the entire string. So let me skip one slide, and let's look at this spec. Okay, so this is even more interesting. I think this is really fascinating, that we're not even going to let X be composable within Y. We're just going to define X as value 1 and value 3, the array. Y is going to be value 0, and then the same 2 values that we defined in X. And Z is going to just have a different one. But we're not going to, like before, where we unshifted onto X, so we know that that data was equivalent. We're going to create 3 different immutable objects, and they're all equal in a very specific way. All the data that we put in there are in a tree, and each tree is trying to reuse and recycle as many objects as possible. This is really powerful that we're going to see why this is so powerful in just a second. But let me take a step back, and this is, again, basic immutable principles is that you cannot change something that you own or that something exists. You can only generate new things. So when we try to change X, we get Y. We don't actually get X as a mutation. And when we try to change Y, we can't change Y. So we get what we try to do in a Z value, and these are equivalent. And again, we created those from themselves, and now we can see that value 1, the first element in Z, is equivalent to value 1 in itself. So he has 2 object reference equal elements. This is really interesting, and let's continue really diving into this. So what's a recycled, what do I mean by recycled objects? That's it. I'm going to create 2 distinct JSON objects. I'm going to call immutable on them, and then they're equal. They have the equivalent data. They're referentially equal. They're triple equals equal. This is amazing, all right? And why is it so amazing? Because now, when we're going to adopt immutability, we're going to be able to consume server-side API, a full JSON payload. We're going to be able to assign it as our new app state and maintain referential equality with only what has changed. If that hasn't sunk in about how important that is, this basically solves a whole idea of trying to do deltas, except that you probably still want to do deltas because of networking. But it is incredibly powerful. And that React can consume this immutable data and then start consuming these reference equality checks. And we're going to see how much that improves things. So here's what immutability looks like within React. Same application, the same models, same components, the same table with a different API. We're now using Immutable.js API, and their sequences are lazy. So we actually we can't just say map. We have to say map into array, actually do the work. But we're going to still take a table and map over rows and create a new row component. That row component is going to create a single row, and he's going to map over his cells, and he's going to defer to the cell component. And then the cell is still just a TD tag with data. There's almost no change here, right? We just changed API frameworks. All right, so what's the impact of this? I mean, this is a pretty small change just to make. All right, here's the impact. This is actually 90 operations a second. And we had, if you remember, a single React component was doing about 10. A multiple React component, which is what we factored into, which we thought we would see more performance, or at least I did when I first started thinking about this, we dropped in half to 3, and let's just call it 5 operations a second. By just switching to immutable data structures, we saw a 200%, a double. I mean, we went from 5 to 90, right? And from the single operation, we went 9 times better. So yeah, it should have been 20 times better. This is pretty important and pretty powerful. And not only that, but we can maintain this, right, from consuming data. That is in memory. I have that data, and I'm just going to change it. I'm just going to update it and then re-render React. But now I can assert through these specifications that I can still consume immutable data, produce a brand new data object, and still get the same performance. That is incredibly powerful. And here's a flame chart. It's still quite long, but each little segment is what took 200 milliseconds plus previously. These are incredible performance gains, and here's what they look like all stacked up against each other. You see that the middle one is the multiple React components, and it is the thickest memory footprint. This isn't even with immutable data, which is supposed to have a high memory footprint. That's what everybody says is a negative against immutable data structures, is that it's more memory intensive. Well, this is Java processing, and we are doing a lot of Java processing, but we're getting so much performance gain that you can't ignore it. So why does this work? What actually happens? And there's some secret sauce that I'm not really showing you, and that's that in the previous two, the single component and the multiple React components, I'm using a pure render mixin. Right? It's an add-on from React, and it's basically trying to check referential quality to try to game React to say, hey, has this component rendered, and does it need to render again? Well, actually, it doesn't need to render again. Based on this data I'm about to give you, do you need to render? Do you need a JavaScript process to produce a new virtual DOM, or can I use your previous virtual DOM? Now, obviously it was failing, and that's not its fault because we actually did change the data, right? The referential quality before in multiple components was wrong. But with immutability, our references are only changed in what you see squiggly lines. So when I change a single cell in an immutable data structure, I get a brand new data structure that only contains differences of referential quality in the single row that was mutated and then in the single cell. So out of 10,000 cells, I have one row to look in and I have one cell to process. That is how we can make such a giant leap from processing time, because that's really all we're dealing with. That's why multiple components was really failing what we thought, is that he was actually having to process a 10,000 row table, just like in the single component. But then he was having to do the bookkeeping that React provides, or that React is doing behind the scenes to manage all those objects and to produce new virtual DOMs. So the final remarks, I guess, are really about immutable app state. And that's that we can really change the performance and change the dynamic within any application, not just React, but within any application we can maintain, if we can switch to an immutable app state, it's just the performance benefits are just undeniable. And then React building, application building with Flux is really where you should be aiming for. So if you're going to build just a view, just play around with React, you don't need to incorporate Flux. Right? If you want to incorporate an application and have a team of developers building, you need something like Flux. And Flux is still in flux, and it is not really, what I would say, defined completely. So be the guy that defines what Flux means. Start playing with this and start thinking about applications and data flow, because unidirectional data flow and not having to think about partial renders and react to data changes is crazy different mindset. It's a very declarative mindset, something that if you're used to D3 or something declarative where you declare all states that could happen and then you just run. You never have to react. You just, if your data is this, then do this, right? It's not about putting something out there and just letting the users change and managing that change. It's about having an application state that completely defines your application. I mean, if you think about that like form serialization back to a server, right? If my application state defines my application, I don't care about touching the DOM. I don't need jQuery at all. I don't use jQuery anymore. I don't need the DOM. All I need is my data. My data is truth. And that's really what this talk is about. Thanks.